in a physical class, we have, I can see your eyes, your face, and I can understand. So here, most of you have not switched turned on your camera, so it will be very difficult to guess like whether you are able to see this or there is some any technical issue like that. So I have to keep on asking you. Okay, so here, yeah, so we have in the last class we have started our discussion with this CMOS, and as I have, before this technical glitch, as I was discussing, this is basically an CMOS inverter. CMOS is the complementary MOSFET transistor, and here we have discussed why you should have PMOS as only the pull-up network and NMOS as the pull-down network, right? As of now, we are considering MOSFET to be a three-terminal device. We are not considering the effect of body terminal, right? And here we have seen how to get the voltage transfer characteristics of this MOSFET. And to do it graphically, we have to notice this point that VDS for this is the PMOS ID VDS characteristics. This is the output characteristics, right? For PMOS, we have to take a note that this is VDS, right? And this VDS is nothing but VDD minus VDS of this N transistor, right? So if you want to superimpose these output characteristics on top of that, so you have to take a note that you have to reverse the sign and you have to substitute it from VDD. Just consider it and you know how to do it. Then just do it. You will get the the voltage transfer characteristics from here from the intersection points. Like that we have done, right? This point, this point. After that, it will go this. So it will start from here, go to here, then this point to this point, right? So, and you can see from here that this from this voltage transfer characteristics, it is quite clear that this point is nothing but VDD, right? So VOH dash is equal to VDD and VOL dash, that is nothing but equal to 0, right? So, and during this state, so that means within this region, this PMOS is on and NMOS is off. So no, there is no static power dissipation. Similarly, during here for this region, right, PMOS is off and NMOS is on, right? So here also there is no static power dissipation, right? Because not both the transistors are simultaneously on. So there is no direct path from zero from this power supply to this ground, right? So these are the key things that you should always remember, right? So here we have also discussed different regions last class, and in different region which transistor is operating in which region. At the last of our at the end of our discussion during our last class, we have mentioned this point. This point is the switching threshold or the logic threshold of the CMOS inverter. And you know how to do it, right? You have to take a straight line, means V in equal to V out on this VTC. The intersection between this VTC and this line would give you the VT, right? And we have mentioned this symbol as this V only T, right? Okay. Now let us discuss a few more things on this, logic or logic threshold or switching threshold, that is VT. So VT means basically this region, right? This region, right? This region. So this falls under the region of this region, right? This region where the gain is very high. And in region 3, both the transistors are in saturation. So if I ask you, can you find what would be what would be the expression, okay, of this VT, right? Then I think you can quickly do it. I am not asking you to do it, but you can always do it with me, as we have lost some time due to this technical glitch. So I will do it quickly. Okay. So we are assuming the MOSFET. MOSFETs are of this long channel. Long channel MOSFET. So why I am saying now that this, we are assuming that these channels are long channel MOSFET, because so far the MOSFET equation that we have learned, that is ID equal to this proportional to this VGS minus VTH whole square in saturation region, that holds for the long channel MOSFET. Okay, if you reduce the channel length significantly, then you have to consider other effects, and those MOSFETs are termed as short channel MOSFET, and the equations that we have learned that are no longer be applicable for those short channel devices. So remember that, okay? So we are doing it for the long channel device MOSFET. So for long channel device MOSFET, so we know here both transistors are in saturation. Both transistors are in saturation. So if both transistors are in saturation, so we can simply just add, I mean, simply just equate these two equations, right? This is Kp by 2. This is VDD minus V in VTHP. Okay, I request you to please take a note of couple of things here. Here, why am I, please note, why am I writing this? Why am I writing this? This is equal to this. Anyone?
So we are replacing VSG by VDD minus VN.
Right, right. So this is basically your VSG, right? Right. This is basically VSG. So VSG, and why I am writing it mod of this VTHP, because VTHP is negative. Right. So that's what I am writing here. This. So this is square. So you now this logic threshold will be or switching threshold or logic threshold will be the input voltage where these two would be equal. So now you can replace V in with this VT, right? So and you can simply find it for which condition it would happen. So V in equal to this VT. So I am not solving it step by step to save some time. Just I am writing the finally what you would get. So it will be VDD, but I request you to please do a cross check of that. So here VTHN root over of this Kn by Kp plus root over of this Kn by Kp, right? So if you solve this, okay, you will get V in, which is nothing but equal to the logic threshold, would be equal to this. Fine. Okay. Now, yes. So here, one thing to notice is that when, say, from for this expression, right? If you consider a situation where VTHN is equal to mod of VTHP, and Kp equal to Kn. If you consider this, so consider Kp equal to Kn, so this is 1, so this is also 1, so denominator become 1, and here these two threshold voltage are equal, so this will cancel with this one, so that means your Vt, then Vt would be equal to Vdd by 2, isn't it? So that means your this point, that is this threshold voltage, would lie exactly in the mid position of from this 0 to VDD, right? Exactly at the mid position, right? And in most cases, this is what we need. Okay, this is actually what we require. In most cases, we generally prefer to keep the threshold voltage almost in the middle of this VDD. Okay, so that we can get a symmetrical VTC, right? Then only VTC will be symmetrical, and if you find the noise margin from here, it is also expected the noise margin would be also similar for these two cases, if this is the case, right? So I am writing here if. Fine. Okay. Then let us okay, you have seen now this, but let us now discuss what would be the effect of this Kn and Kp. Let us say that threshold voltage of MOSFET and N channel MOSFET and threshold voltage of P channel MOSFET, you are able to make them equal. Okay, no issue in that. But if what would be the effect of this Kp and Kn, right? Okay, before I discuss this part here, one thing, maybe one more thing here I should tell you right now only. So this Kp equal to Kn, right? What do you mean by Kp? Okay, what is the expression of Kp? Kp is mu P Cox W by L for this PMOS, right? What is this Kn? Kn is mu N Cox W by L of N, isn't it? Okay. Now you see this Cox, as I told you, whether you are making NMOS or PMOS, if they are on the same technology node, then the oxide thickness is going to be the same. If oxide thickness, right, Tox or oxide thickness same for NMOS and PMOS. If oxide thickness are same, then Cox is basically equal to Tox by epsilon ox, right? Since Cox would be also the same, right? So that way Cox would cancel out. And if you now take the ratio of W by L of this NMOS and W by L ratio of this PMOS, then you see what you will get. This is P is here, right? P. So you will be here this mu P, right, divided by mu N. This mu P by mu N, isn't it? Okay. Now again, what is L? L is the gate length, right? For a particular technology node, L is also the same. Okay. So that way you can say this Wn by Wp would be equal to mu p by mu n. And do you know generally what is this ratio for silicon?
Sir, mobility of electrons is around 2 to 3 times
Right, two to three
mobility of
times. So that, yeah. So
Is
that way,
roughly how?
yeah, actually it depends. Okay, again, this whether it will be 2, 3 or less than 2, that again depend on the which technology you are referring to. Mobility depends on a couple of other things. Maybe those discussion we will take later on. But as of now, we let us say that it is from 2 to 3. It is not 2 minus 3, it is from 2 to 3. Okay. So that way you can understand that in order to make Kp equal to Kn or VTC symmetric, what you have to do, you have to make Wp equal to 2 to 3 into Wn. Have you understood? So that is the reason why you have to make with the PMOS with at least 2 to 3 times of that of this NMOS, right? So in order to get the symmetric inverter, to get the symmetric inverter. Fine. Okay. Now let us come to here. Then what is the effect? So you have understood, like in order to get the symmetric inverter, right, you have to have this condition, right, means Kp equal to Kn. But suppose you don't want to, you don't care, you don't want to make a symmetric inverter, but just want to see that what is the effect of this Kp and Kn, all this on this voltage transfer characteristics. Then can you give me some uh, some of your explanation that, okay, say I want to make Kp by Kn by Kp higher. Any guess what will happen to this VTC?
So the graph should
Graph
bend
should
leftwards.
graph should bend leftward. This
Uh,
side, this side.
yes, sir.
Okay. Yeah, you are right. But could you please explain why?
Sir, because like how should I explain?
Hmm.
So give me
No, you
time,
have
sir.
to. You have to. You have to explain, right?
Yeah, I have to explain, but I'm just thinking of correct words.
Okay. Then please think and
Uh,
then tell, but bit
yeah,
quickly.
yeah.
Yeah. Anyone else would like to try as well?
Sir, that above equation which you have written, Vn is equal to Vt. So
Mm-hmm.
from there we can observe like if we increase Kn by Kp,
Mm-hmm.
then we can see that uh, for for obtaining for obtaining the sub threshold voltage,
This is
if
not
the
subthreshold
subthreshold,
voltage.
I
This is
mean,
not
sorry,
subthreshold threshold.
the voltage sorry, the voltage at which both we, uh, for
Both,
which we obtain the third region. I don't
right, right.
remember the name. So
Yeah,
that
this
if
region.
that point,
Right.
yeah. So if that point shifts towards left, then according to that, the graph should shift toward left. And from that equation, we can see that k, if we increase kn by kp, then vn will reduce. So
Right. So Kp by Kn higher, then what you are saying, then Vt approaches or not higher. Uh, if say it's not a good word to say higher. So suppose if Kp is Kp Kn by Kp is greater than 1, right? Then this Vt approaches towards 0. That means you will get a characteristics which would be something like this. Okay.
so can you tell the name of the VT again? Like I forgot. Like what's VT
This
called?
one, this Vt is called the logic threshold or switching threshold.
Okay, okay.
Hmm, right? And that I think you, as your friend explained, right? You can also explain it from this equation, right? So similarly, on the other way, if you make Kp by Kn less than 1, then Vt approaches towards VDD, right? So it will means it will shift in this side, right? Fine. Okay. So I hope you have understood from this equation that why this is happening, right? Okay. Great. So you know then if you means while you are designing some inverter, then you know that if you so what is this Kp by Kp by K Kn by Kp actually this ratio? This ratio basically indicates the width of the transistor. And as a designer, you have a full control on that. You can give any width as long as that you are falling under that particular rule, right? So your width as a designer you can change. So you can change the width and you can fix this value of Kp by Kn. Now if some depending on some requirement, you know how there's a what is the thumb rule to tweak this threshold voltage or shift this VTC either this side towards 0 or towards VDD. Right? Okay. So this is from this equation and that is fine. Okay, absolutely. But could you please also explain any other way, like why this should happen? Okay. Means any other way, any other thought, some like physically whatever else we have discussed based on that.
So basically, if we just increase, I mean, if Kn by Kp is greater than 1, then actually
Right.
Kn is greater than Kp.
Right.
So
Kn,
for
yes, actually,
K
and then you are
is
saying,
greater
okay,
than Kp. Then
let me
for
also write it. You are saying Kp by Kn by Kp, if it is greater than 1, so that
Kn
means
greater
Kn
than
is greater than Kp, absolutely.
so
Then
so for so for same current, we have to have more VGS for the PMOS than the NMOS.
more VGS for the PMOS than the NMOS, absolutely right.
So more VGS for PMOS means Vin should decrease,
Vin should decrease, absolutely right.
and that's why the whole curve shifts
The whole curve
towards the
shift towards
zero.
this, right? Absolutely, I agree with you. But maybe you are right. But I would like to explain it from this point of view. See, the VGS is actually not changing here. Na? VGS is fixed, right? Means all the gate voltage is fixed, right? Gate voltage is same. Whatever the applied voltage is same for this PMOS as well as for the NMOS, right? But what you are doing, you are increasing this Kn value, right? So what do you mean by increasing Kn value? Okay, now see this equation, ID equation. ID is proportional to Kn only, right? Again, IDN actually. IDN proportional to N. This is also proportional to Kp. Kn and Kp, right? You make the
Yes.
transistor with current increases. So that means for the same VG, okay, that means for same VG, ID will be higher, right? For NMOS, ID will be higher for NMOS. So that means, previously we have seen when this Kp and this equal to Kn, for a same gate voltage, for the same gate overdrive, I would say, for the same gate overdrive means Vg minus V threshold. Okay, that how much we are going above to the threshold, right? You please think it from for the in the context of NMOS as well as for the in the context of PMOS. But let us say for the time being we are fixing the PMOS. We are not changing the PMOS. We are only increasing the NMOS width. So NMOS current is increasing. So for example, earlier you have seen here that the first the intersection was this, second intersection was there, third intersection was this, fourth intersection was here, right? And so that means you can see this is for what? This is for 1 volt. So that means there is switching is happening. Switching is happening when? Switching is happening between 1 volt to 1.5 volt. You see here threshold VDD, right? VDD is equal to 2.5 volt, and you are getting a switching between 1 to 1.5, 1 to 1.5, right? However, now you have increased this gain. So what will happen to this line, to each line? So each line will now be shifted upward, right? This line has now shifted upward. This line, the next black line, this has also shifted upward, right? So previously for the black line, you have seen this is the intersection of this PMOS and NMOS. So for this, after this point was changing, transferring from this side to this side, right? Means there is a switching of in the output side. But here you see, to get the previous previous black line, right? You need lower VGS. You need lower VGS to achieve now this, because you have increased this Kn, right? So that means if earlier you need this much voltage, earlier if you need this much voltage, for this case you will need lower VG, right? Lower VG to get this transition from this region to this region, right? Is this explanation making some sense to you? Shubhayun?
Yes, sir. Yes.
Okay. Okay then. So this is another way of thinking, physically, right? What is happening actually inside this. Okay. Now quickly, as we have discussed for all other inverters, so find the noise margin of a CMOS inverter. So how to do it? It is pretty straightforward rule, right? And almost for all the cases we have done this, right? So this is the point where corresponding to VIL and output is VOH. This is VOL, this is VIH. And the criteria is here, the slope would become equal to -1, right? So that is the criteria. So then to find this VIL, okay, then let us say calculation of, or calculation, not calculation, it is not, we're not calculating. So finding the VIL and VOH. Okay, so please tell me, how should we approach?
So for VIL, the NMOS is in saturation and PMOS is in linear. So we'll equate
Okay,
them.
NMOS in saturation, PMOS
Triode. Linear.
in triode, right? So you know the equations. So equate the equations. So just I will not do it completely. So it is VGS minus VTH. VTH in square would be equal to, this is PMOS is in triode. So this is equal to VGS minus VTHP into VDSP minus VDS square by 2, right? So you should know like which one is what, right? Then here, what you can substitute from here, just a quick thing. So VGS is basically that V in VTHN square KP. Okay, now. Yeah, now,
VDD minus VN.
sorry.
VDD minus VN.
Yeah, VDD minus, right. Should it be VDD minus V in, or should it be V in, which way? Please think. We are writing here.
Okay.
Have I written it correctly? Is it?
So if we had written VSG and then outside we had written VSD, then also it will be same, but then the value would be VDD minus VN, and now it will be VN minus VDD.
So now it will be V in minus VDD. Okay. So V in minus VDD. Right. Now it is VTHP. Right. And what is this VDSP? This is V out minus VDD. And here it is V out minus VDD square. Right. So this is basically one
Sir,
equation.
So by
so then VTHP will be plus.
I yeah, sorry.
And then VTHP will be plus because means
V
VGS minus VTH or
VTH would be plus. You are saying this one would be plus.
VT. Yes, sir. VTHP will be plus because it is negative.
So it is negative. Should it be plus? Do all of you agree?
so it will be minus only.
There
So
should
it
be a
will be
mod,
minus.
but there should be a mod over there.
Where should be a mod? Where should be a mod? On here?
So basically, every quantity should be positive, right?
Every quantity should be positive, right?
Like V in minus VDD minus VTHP, this whole term should be positive. V out minus VDD, this whole term should be positive. I mean,
Right.
if they are negative, also we have to take the mod. That is the thing,
Okay.
right?
So is it correct now?
So we don't have to give the mod there because
Yes,
VGS
sir.
is negative and
Sir,
VTH is
they are
negative.
The
Minus
VDSP is negative
yes,
and like all the terms as they are negative, so we don't have to give mod.
Okay.
yes.
So this is a simple calculation. You can I think do it, right? So here what means, what is the important thing? Important thing is that this, you write this, the equation, write it properly with proper sign. Okay. Then just you will get one equation. Okay. Second, you have to find dv out by dv in. This relation gives you that dv out and the relation between v out and v in. So find it. Right. So once you have find this dv out by dv in, make it equal to -1, right? And there you will get another relation between v in and v out. So now you have two equations, right? So let me write that equation. So I will not uh, do it means completely, but this is expected to be something like this. These equations are pretty big actually. This V out minus VDD plus VTHP plus KN KP VTHN 1 plus Kn by Kp. Right? Now you see this equation and this equation, right? But this equation, VIL equation, you have V out, right? Here you have V in. So V in is basically here VIL, right? So but if you solve equation 1 and equation 2, right, you have two equations, two unknowns, VIL and this V out. V out is basically here VOH, right? So V out is basically here VOH, right? V out is here basically VOH. You have two unknowns, two equations, you can solve it and you can find the analytical expression of VOH and VIL. Find VIL and VOH from 1 and 2, right? It's quite straightforward, right? It's such a simply, you have to just solve it. Okay. Then what about this VIH and VOL?
NMOS in triode and PMOS in saturation.
Right. NMOS in triode and PMOS in saturation. So I thought I have kept some space, but looks like I have not. So here we have to write this one, finding VOL and VOL and VIH and VIH, right? So in this case, NMOS, please say it again, NMOS in which region?
So NMOS in triode.
NMOS in triode. And PMOS?
Saturation.
Saturation, right? Same process as done for VIOH and VIL, right? So that way you know VOL, VIH, you know VIL, you will get VOH. So if you know all four, then find noise margin high and noise margin low, right? Right. So you can see the equations, right? And then you have to solve this equation with this equation. Same thing, you have to do it here, right? And remember, we are still using this equation, okay, in saturation for MOSFET, which does not include the channel length modulation effect. Means if you would have considered the channel length modulation effect, then you would have another term here, which is 1 plus lambda VDS, right? So then you can think, basically lambda VDS means lambda V out, right? So you can think again, like, what would be, how difficult it would be to do it, with your means by doing the hand calculation, right? So for this type of exact solutions, only the advisable way is to go within simulator. Okay, simulator can do all this process very quickly. Okay, but here the basic understanding is that, like, you should know how to do it. If you have to do, you can make some approximation for hand calculation and get the quick results, right? So I hope you should be able to find the noise margin in a CMOS inverter, right? We are not doing the complete calculation because it is type of, again, the repetitive thing, right? Like as we have done for the other things. If you want to see, it is given in the Kang's book. You can, if you want to follow it from there. Okay, now few more points regarding this CMOS inverter, and which is quite important. So first thing is, this is the CMOS inverter, right? Here is this V in and here is the V out, and we have couple of times plotted this V out versus V in, which is also called the VTC, voltage transfer characteristics, right? And it looks something like this, right? Here we know, we have noticed couple of things, right? For example, like this is 0 voltage, this is V threshold voltage for NMOS, right? And this is VDD minus threshold voltage of PMOS, right? This point, and this is VDD. This point is the switching threshold, right? This point is the switching threshold or VT, isn't it? Okay, fine. And we have also noticed from here, during there is no static power dissipation, because VDD is here, the highest voltage is VDD, lowest voltage is 0, and at the same time when this PMOS is on, NMOS is off, and the vice versa. So there is no static power dissipation 0. Again, I am putting on star here because ideally it is actually, I mean, practically it is not 0. Ideally it is 0 because MOSFET does have some leakage current. So as a result, you will have some static power dissipation as well. But it is not due to that this transistor is on, both the transistors are on at the same time, right? So static power dissipation is 0. Okay. Now, if I ask you from this point, after this point, that please tell me how, if I want to plot the drain current versus this input voltage, versus, right? So I want to plot drain current, and you know the drain current for NMOS and PMOS would be the equal, same, right? Same current has to flow through this, right? If and if you want to, if I ask you to plot this ID versus V in, could you comment like how does that plot look like? Would it be 0 always, or how does it look like?
Sir, I have a doubt in first graph.
Yeah,
Like, how much does that region 3 last in seconds? Can you give idea? Like, how much does transition period in time?
this is not time, na? This is x-axis is V in,
No, sir, I'm saying like if I switch 0 to 1, then
right?
approximately how
Then it
much?
again, okay. Then that depends on the delay.
Okay,
Like suppose if you were giving here some input, which is always input also have some delay, right? Right. And so obviously, this is the transition time at the input side. And on top of this, there is an RC delay from this as well. So this we will discuss, later on. Don't worry. Okay. So
okay.
definitely there will be a significant delay. Okay, in this transition. Okay.
So because in
Well,
region 3, static power dissipation will not be 0, right?
in region 3, static power dissipation would not be 0. You are absolutely right. Can you
Yeah.
explain why in region 3 there will be no static power dissipation?
So because it will be short circuit.
It will be short circuit because in region 3, you see both transistors are in saturation, right?
Yeah.
So in this region, both transistors are in saturations, right? Both are in saturation. Both PMOS and NMOS are on, right? And in saturation, right? In this region here, right? So obviously there will be some static power dissipation, okay, during this region. Okay. So what about this region from here to here? Will there be any static power dissipation here as well?
No, sir.
Why no?
Yes, but lower
Yes,
one.
Okay. Yeah,
yes.
okay.
See, because only for this region the NMOS is off, right?
Yeah,
Only for
right,
this
right.
region the NMOS is off. Only for this region the PMOS is off, right? Other than this region, here completely NMOS, PMOS is on, right? Again, outside from here till this point, again here in all regions NMOS is on. So then will there be any static power dissipation here?
Yes, sir.
Yes. Then on the same token, will there be any static power dissipation in this region?
Yes.
Yes. So that's what we have said, like static power dissipation is 0. Static power dissipation, we mean this region and this region.
Okay.
Okay. Because at the input have some limitation, right? Input can be like near to 0 volt or near to this VDD, right? So if you exceed that VTH or VTHP from both sides, then there will be some static power dissipation. Okay. Now let us come to this point, right? What I asked, like if I have to draw this drain current versus V in, now you know where the transistor are, means where the transistors are on and off, right? So please give me and hint where how this curve should look like.
It is like U shape
Like U shape, is it be U shape? Okay, where the current would be maximum?
for the mid region.
Region 3.
VT.
At VT, right? So obviously at VT, so say this is the maximum current. At VT, the current would be maximum. Okay. So from VT till this point means within this region, the transistor is in which mode? Means both transistors are in what? Saturation, triode, which region?
Saturation.
Saturation region. And so in saturation region means ID, either P or N, right? You know, both are VGS minus VTH square, isn't it? For both, either PMOS or NMOS, both for both, it is VGS minus VTH square. Okay. So what is VGS? VGS is basically V in. So you can see here, during this region, means in this region, the expression for this ID with V in, so this is basically V in, is an square law, right? So if you say, then from this region to this region, say like this point, right? This point and this point. So I am right saying it like A and B. So say this is A and this is B, and say this is that VT, right? So here the current would be highest, right? Here the current would be highest, and here. So from here till here, or from here till here, there that it will be a type of which shape? It will be type of, it is not be linear. You understand my point, right? It will not be a linear one, right? It should, because it is square, right? ID is proportional to I in square in this region. So it would be like this. Okay. What about in this region? In this region?
It will
In
decrease
this region is what?
and go to
Uh,
0.
yeah, but in this region, what should be the shape? Like straight line, what? It will be mostly straight line, because see, at least one of the transistor would be in the linear region, and in linear region, it is basically a straight line equation, right? Right? And beyond this, like below this and beyond this, the current would become 0, right? So this is 0, this is VTHN, this is VDD minus VTHP. Again, I should put a mod here, right? Mod VTHP. This is VDD, right? And this is ID max, right? So you have understood. We are saying the static power dissipation is not there. Means the static power dissipation is 0. But when you are doing the transition, okay, so this is called the dynamic power dissipation. So dynamic power dissipation does exist. Okay, dynamic power dissipation means when you are doing any transition, either from 0 to 1 or from 1 to 0, uh, 1 to 0, or you are doing a transition from 0 to 1, right? For either case, right, you have to cross this region, and at that time there is a direct path from output to input, means VDD to not output to input, from VDD to ground, and there will be power dissipation. So CMOS will be good, almost no power dissipation, as long as you are not changing the input. Unlike in earlier cases. Earlier cases, if you keep also at 0 or 1, in either, you have seen, for at least for one of the cases, there will be a direct path between VDD to ground. Right? And that is not there. That is, we are able to completely avoid here. Right? Okay. Right. So on the same context, then let us also discuss what would be the gain. Right? So what would be the gain plot if I again plot it like gain versus V in? Any guess? Any comment?
Sir, I have a question.
Yeah.
Does this point A and point B coincide?
Point
Accord-
A and point B coincide. You
If
okay? What
if you
what do you think?
neglect if
Okay,
we
what you? Huh.
if we neglect the lambda, then they should coincide with the ideal
Exactly,
equation.
exactly. If we neglect lambda, then as per this theoretical whatever we are doing, because if you see this, right, then the crossover, okay, from here to here would be on the same line, right? You are right.
Yes.
So theoretically, if we, but for practical case, we never get and parallel lines like this. So you always have some upward slope. As a result, we will have this thing different. So to make it generalize, we always differentiate between point A and point B.
Okay. Okay.
Okay. Okay. So yeah, can you comment on the gain? Where the gain is maximum?
In region 3.
in region 3, right? Because gain is what? V out versus V in. So where the slope is highest. So the slope is again highest here, right? So again say that this is the end point, right, between say this point A and point B. So again here the gain is something like this, right? And from here to here the gain will then fall down, and here it is fall down again. This is VTHN, this is VDD minus mod of VTHP. This is VDD, this is 0, right? So if you want to make and say amplifier in analog domain, then probably you would use it. Think of, you can probably think of using this as an amplifier, right? If you can think, please do read. This is a very interesting thing, that whether this CMOS inverter, can you use the CMOS inverter as an amplifier or not? So can you use CMOS, use a CMOS inverter as an amplifier or not? Okay, and do comment in the next class that whether you can use it or not, and if yes, then how? Because see, this region is very narrow, so obviously this width, right, this width is very narrow, right? So if you go from this region to this region, your gain will significantly reduce. If you go to this region, your gain will significantly reduce, and even in this region also gain is not constant. So please do comment on this question, that can you use this CMOS inverter as an analog amplifier or not? If yes, then how? Right? Okay, just to give a thought for the next class, that is tomorrow's class. That is tomorrow we are going to start from here. That is the scaling of supply voltage. So for example, here this is an CMOS inverter. So here you can see VDD is 2.5 volt supply voltage. So what will happen? Suppose and the threshold voltage of this PMOS is say minus 0.5, and this is for say plus 0.5. So what will happen if you now reduce it, say from 1.5 to 1.1, 2.5 to 1.5 volt? What will happen? We have to see that, right? What will happen if you go make to 1 volt? Okay, we do not know. We have to check it. What will happen if we make it 0.8? Or eventually, what will happen if we make it 0.2 volt? Is this device still work? Is this inverter still work? Is this total thing will still work as an inverter or not? Okay, so this is called the robustness of this of this inverter, and we'll see in the next class that whether this inverter on this particular design would work or not with reducing the supply voltages, and we'll also see that why we need to reduce the supply voltage or this VDD, what are the requirements or what are the positive points if we do it, right? And at the same time, we'll also see nothing comes free, right? If you are getting some advantage, then obviously in some other place you have to pay the price. So we have to also see what are the prices that we have to pay, right, for doing that. So I think with this we will end here. It's already 1. You definitely have some lab after this lunch break. Okay, so again, thank you all. So I will see you tomorrow.